Hello, my name is Alexander Bauer, and what follows is a summary of my semester's computer vision research. Before I begin in earnest, here are some pictures of my house. There are electronics on the floor and glassware on the table. To me, this looks like it needs some cleaning, but not to everyone. This is a very subjective call, and can be a source of contention between cohabitants. Standards of cleanliness vary wildly. Clutter to me may not be clutter to you. As a result, we may disagree on how often to clean and how thoroughly to do so. By quantifying clutter quickly and automatically, we can agree on when and what to clean, as well as establish routines and track trends over time. But how do we do this? For humans, context is very important. Pillows on the floor might need to be picked up, but pillows on the couch might not. A napkin holder on the table might be meant to stay there. Providing this context into a visual clutter classifier is an extremely hard problem, to say nothing of the object recognition capabilities necessary to apply them. So, we must settle for simpler heuristics. Looking at this picture, it's easy for us to identify discrete objects which should be removed: the watermelon and the cutting board, the serving tray, and the soda can. These are highly textured spots, particularly this box of small candies. Compared to other flatter areas in this image, the edges are very close together. Hence, I want to find regions which are visually denser than average. The implementation of this heuristic which I explored is edge density. I began looking at the canny edge domain. This color image is converted to grayscale and redrawn as just edges using the OpenCV canny edge detector implementation. This acts as a sort of first-pass thresholding. Flat areas are largely removed. Next, I look at the density of white pixels in this edge domain. To do this, I used the built-in box filter implementation in OpenCV. The result looks like a blurred version of the original and exhibits visual artifacts discussed in class. I saw little difference using a Gaussian filter, other than the elimination of the artifacts, but these have no effect on the final results. A better implementation might be capable of counting discrete lines in this space, or using oriented gradients to find regions which have many edges in different directions. Next, I used adaptive Gaussian thresholding to find the brightest and hence densest parts of this image. It is important to use adaptive thresholding, because a constant threshold yields very different results on images taken at different distances from the study area, and on different scenes. Next, I used OpenCV to estimate contour polygons that surround each region, and found the convex hulls of each. This simplifies the result prediction area, and better matches the actual shapes of the objects it observes. The white regions on the right are the final predictions for the cluttered regions, and here they are overlaid on the original image. Clearly, there are a large number of false positives, including the painting on the wall, the air conditioner, and my roommate Mark. However, it successfully identifies all of the clutter items, including some that are hard to see, such as the power strip underneath the couch. On the left, we see the table again. The small candies, watermelon, serving tray, and small figurines are all classified as clutter. On the right, all of the stray dishes and appliances on the counter are marked, in addition to a handful of false positives, such as the microwave. Clearly, this technique is somewhat primitive, and there are improvements to be made. Many kinds of false positives need to be stamped out. Texture is another large piece of the puzzle which remains totally unutilized. For images from fixed cameras, machine learning or a simpler technique could be used to mask out frequent false positives, such as the wall hangings shown earlier. But I look forward to future applications of this technique. For home automation, quantification of clutter using commodity hardware opens up many possibilities. Reminders could be set for individuals to pick up, and automatic cleaning processes, such as robotic vacuums, could be triggered. Additionally, parks and public landmarks could benefit from automatic identification and location of litter, trash, and other out-of-place items. These could be identified in pictures from unmanned survey drones or in publicly available pictures with geotags, such as from Flickr. This concludes this presentation of the dense edge detection as a clutter classification technique. Thank you.